All right, let's talk about chemistry then. Last time when we were talking about ionic substitution reactions, I introduced the idea of an SN2 reaction, which is a substitution reaction at an sp3 carbon in which the carbon nucleophile bond forming event occurs at the same time as the carbon leaving group bond forming event or bond breaking event occurs. So we have a transition state. We kind of rationalized what its structure looked like. We said the nucleophile has a partial bond to the carbon and there's a delta minus because it starts as negative and ends up as neutral. It's somewhere in between. The leaving group is in the process of leaving. It starts as neutral and ends up at negative, so it's somewhere in between. And we talked about why the hydrogens are approximately planar. In other words, why the carbon has a trigonal bipyramidal arrangement, because that's the best way to arrange 5 things around a carbon, get them as far away from each other in space as possible. But one thing I did say that I just kind of threw up on the board without rationalizing was the nucleophile carbon leaving group bond angle of 180 degrees. In other words, why is their backside attack? Or did I just kind of do this at random? So we thought about that and said, well, maybe the reason there is this 180 degrees backside attack as opposed to, say, attacking from the same face that the nucleophile is on is because these delta minuses in the transition state on the nucleophile and the leaving group being the same charge would repel. They want to be as far away from each other as possible. And if you just want to kind of model that, imagine your hands are the nucleophile and the leaving group. How do you get them as far away from each other as possible? You put them out here, 180 degrees apart. So we started talking last time about an experiment to test that idea, to test this electrostatic issue in the transition state. So the experiment we're going to look at is a case where the nucleophile and the leaving group have opposite charges. So in other words, if charge is an issue in controlling the structure of the transition state, this guy, since it would have an opposite charges here, they should want to be on the same face potentially. So what we did last time is drew out the transition states, which I'm going to do again here. And I encourage you to think about the nature of the product. So let's start with this. We'll call this the front side transition state, and this is the back side. So on the front side, nucleophile is coming in from the same face that the leaving group is on. There's our leaving group leaving. Now delta plus, because it's got a positive, but it's beginning to accept some electrons. There's our nucleophile with its delta minus. And the benzene ring pH, by the way, maybe I could write that over here. pH equals phenyl. That's a common abbreviation for a benzene ring with one attachment. Don't confuse that with phenol, which is a benzene ring that has an OH on it. Or for you cooking mavens, don't confuse it with F-E-N-N-I-L, phenyl, which is a spice. So there is our transition state. And its structure it's got kind of the same idea about groups moving out of the way as we had in our methyl chloride transition state, except that the groups attached to the carbon, instead of kind of flipping in one direction or the other, because the nucleophile is coming in here, they're going to move back like so. We'll draw that product of that in a second. And then we have the backside transition state, which is going to look a lot like this guy over here. There is our nucleophile coming in, carbon leaving group leaving, and then the things attached to benzene ring, the methyl group, and the hydrogen. There's our transition state. Now, key to figuring out what the structure of the products looks like, we can see that a carbon nucleophile bond is being formed, and we can see that a carbon leaving group bond is breaking. But key to seeing what happens to the other groups is to think about how they move as the reaction moves through going from the reactants to the products. Now, I've never quite done it this way with the document camera, so let's see if I can make it work. All right. So this is our model. Now this is our sp3 carbon. It's tetrahedral. We use green here for the leaving group. So there you can see there's the leaving group. There's the things attached. And what the things are attached is unimportant, really. We're just being kind of generic and using a sphere, a blue thing, and a red thing. So maybe one of those is a benzene, a methyl, a hydrogen. Doesn't really matter for the sake of this discussion. Now what we're going to do here is think about what happens when the nucleophile, there's our nucleophile, the nucleophile approaches. Now we said that we're going to talk about it approaching from the backside. It's kind of hard to do front side with these, but I can do backside easily enough. So here's the backside coming in. There's the nucleophile's perspective. right? There's the leaving group. There's the carbon. Nucleophile's coming in like this. So here's the nucleophile coming in. Now what happens when the nucleophile approaches these guys? Imagine this is the park bench. There's already 4 people sitting on it. They occupy the entire bench. A 5th person comes along, wants to sit on the bench. What do you do if you're polite? You move away. So these things, doesn't look very good. These things kind of move, flatten out as the nucleophile approaches. So these things move away. You can do this with your model. So the end is they end up moving and becoming kind of flat. In other words, they end up looking kind of like that. Now what I've done is I started with a tetrahedral trigonal sp3 carbon, and I used now an sp2 trigonal planar carbon. So if you have this particular model kit, you start with the dark black ones and end up with the gray ones. So these are squished. Squished, that's actually mushed is our official term, but because I call this the mushed model demonstration. You can call it squished if you like. So here's the nucleophile that comes in. It forms the bond. Now bear in mind, it doesn't happen. It's not these groups move over, wait a while, and then the nucleophile comes in. What's happening is these groups are moving at the same time in response to the nucleophile coming in. But there's your transition state model. Nucleophile coming in, leaving group leaving. Now the advantage to this is when it comes to looking at more sophisticated transition states, or a question on the exam that says draw a transition state, you can take this model and put it in any perspective you'd like and draw what you see. So instead of, in the beginning we end up with a lot of nucleophiles on the left and leaving groups on the right. And I just kind of do that in the beginning to give you a feeling for what they look like. But later on you'll see them drawn in different ways. There's no rule that says you have to draw it in any particular orientation. But using the model of the transition state that we've just made, you can move it in any direction you'd like. All right, now, so let's see what the product looks like. So as the nucleophile is coming in, at the same time, our leaving group, we decided that was green here, our leaving group is leaving, so that's going away. That creates space out here. And so what do these guys do in respond to that available space? Go back to the park bench metaphor. At the same time somebody else is sitting down, new person's coming in, another person is leaving. So what do you do with that space that's opening up with the person that's leaving? You move in to take that space. So these guys are going to move in to take this space. They're going to move in this direction, and the transition state carbon is going to go back from being sp2. It started sp3. It was sp2 in the transition state, and now it's going to go back to tetrahedral, sp3. So it will become looking like this, right? All I've done is, oops, let's get the right model. Since gray was my nucleophile. So there's the thing coming in, and as these groups move, we'll end up with something that looks like this. So it's exactly the same thing. I just move the groups out to being tetrahedral. And so there is the model of the product, and I can figure out what it looks like. Now, key to making this work is to make sure that when you make the mushed version of the reactant, so this thing, right, the flat thing, make sure that you don't do what I did. There we go. Make sure that the groups that are attached, the sequence that you have the groups attached in the reactant are the same as they are in the transition state. Because these bonds don't break. This is the one that breaks. That was our leaving group. So these guys don't break. So the sequence, in this case, clockwise of red, dark blue to light blue is clockwise, so it needs to be the same thing here. If you get them backwards, then you'll get a different product. All right, so that's how you can do this. Now, using this idea, what I want to compare, if I didn't mess up my models, quick check, yes I did. Oh heck, what am I doing now? There we go, okay. So this is, it doesn't matter where we started. I think this is the one where we started, that was our leaving group. That's our product. So here's the nucleophile that came in. Now what I want you to see, what I want you to compare is the positions of these groups. In the starting material, these groups are kind of pointing concave towards the board, and in the product they're pointing concave but in the opposite direction. Think of this, and this flipping of the groups, which by the way we call inversion, this flipping of the groups is like an umbrella flipping in the wind. Not that we know about wind or umbrellas here in Southern California. We don't even know about snowshoes apparently either, like they do in Georgia and places like that. But this is a consequence of the nucleophile coming in the backside and the groups attached to the carbon moving. Now, with that idea in mind, we can turn this thing off. So for this thing, we did the back side up here with the model. So what it means is that as the azide comes in from the back, the groups that were pointing in this direction now end up pointing in this direction. Here is what the product looks like. And this is the thing you probably, if you did the exercise I asked you to do, this is what you would have come up with. That particular structure. Now, the attack from the front side causes the groups that are attached to the carbon to move away, but when the leaving group leaves, they move right back into the same space they were in. So it's like the umbrella getting blown by the wind, pushed back but not flipped over. So that product will look like that. There's your phenyl, there's your N3, because it came in from that face. There's the methyl group, bless you, there's the hydrogen. Now, I said when it comes in from the backside, the position of the groups is inverted, so that's the inversion product. And in this case, where it comes in from the front side, the position of the groups, the stereochemistry, like whether it's R or S, for example, is the same, because all I've done is basically taken the leaving group away, put the azide there, but all the groups stay in the same position. And when that happens, we call that retention. Now, it is the structure of these two products which gives us an indication of what's going on in the transition state, because these two products have a special relationship that allows us to measure the product of the reaction and decide whether the transition state is backside, attack, or elsewise. What's the relationship between these guys? First, are they isomers? Well, enantiomers are kind of isomers, right? Are they isomers? Do they have the same formula? Yes. Are they constitutional isomers? Do they differ in the sequence in which the atoms are attached to each other? No. Are they configurational isomers? Can I take one of these molecules simply by rotating around a bond and make it look like the other one? The answer to that is no. If you play with models, you will see that. But they are isomers, and they're not identical, so that leaves them to be stereoisomers. And they are, as you can convince yourself with models, non-superposable mirror images. So therefore, the relationship between these two guys is enantiomers. There and there. Or this one and this one, actually, would be a better way to say it. One thing we can measure that's a difference between enantiomers is the direction in which they rotate plane polarized light. So by knowing that, and the people who did this experiment made the two molecules separately and measured their rotation, so they could figure out when they took this guy, optically active to begin with, and did this reaction, they got a product that was optically active, and they could measure whether its rotation was plus or minus to figure out what was going on. In other words, was there retention or inversion? So here's the conclusion from all of this. If this charge is controlling the transition state, what would happen? If charge is controlling, we would expect front side attack, because that puts the opposite charges, negative and positive, on the same face. Here we would have negative and positive on opposite faces, and that's not good. We want to put like charges close to each other. But when they went into the lab and did the experiment, they discovered this is actually the product. And any variation you do on an SN2 reaction, the methyl chloride plus hydroxide, this guy, any one of another gazillion SN2 reactions that have been studied, inversion always, always, always happens. So what that means is this is not what's in charge. Maybe it helps in this case, but it's not in charge all the time. So what we need is another thought process, another rationalization for that. So why do we get backside attack? Why do we get inversion all the time? And the rationale comes from this. It's kind of quantum mechanical, but we'll keep it nice and simple. We're talking about the geometry of the attack relative to the carbon leaving group bond. Yes, there's other things attached. We're not going to worry about those. We're just going to talk about the carbon leaving group bond. That's all we need to talk about. When the nucleophile comes along, usually with its pair of electrons, for the reaction to occur, orbitals interact with orbitals. Most of the time when the nucleophile, that's going to be something that looks kind of like this. It is usually a lone pair. Not always, but most of the time, it's a lone pair kind of orbital. So that's usually going to be a P or an sp2 or something like that. So that sticks out in space. Now it has to interact with orbitals that correspond to the carbon-leaving group bond. And a sigma bond, very simplistically put, has two orbitals associated with it. There is a orbital whose electron density is between the atoms that are involved. In other words, it's the one that represents the sigma, the covalent bond. We call that the sigma bond. But there is another orbital that exists because of the way quantum mechanics works. And that orbital has its orbital lobes completely on the opposite side. Let me shade the sigma star, or the sigma, so we can see where it looks. This other orbital, it's called sigma star. The star means antibonding, has a lobe here and a lobe here. And the lobes of the antibonding, the against bonding, point in completely opposite directions. Metaphor, here's a way to think about it. When you are in a relationship and you like someone, you face them. It makes you stable, it makes you happy. When you don't want to talk to that person anymore, what do you do besides defriend them? What do? You turn your back on them. That's what's going on here. This is a circumstance where it's against the bond. The orbitals kind of turn their backs on each other and go, la, 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 I'm not interested. So this orbital lobe is out here. This orbital lobe is out here. Now we need to make a bond between the nucleophile and the carbon, so this is the lobe we interact with. And because this lobe is fattest, has its biggest volume of space right behind, immediately behind the carbon-leaving group bond, that's where we interact with it. So the nucleophile's lone pair orbital interacts with this sigma star lobe right here. And because the sigma star lobe is on the backside of the carbon-leaving group bond, that's where the nucleophile comes. That's the origin of backside attack. This works regardless of what the charge on the leaving group and or the nucleophile is. This is simply an orbital kind of argument. It has nothing to do with crowding. It really doesn't have to do with anything else. It's just that simple orbital argument. And I'm going to point out, just to before we leave this issue, that this is a simplification. The actual orbital picture is much more complicated, but it gives you a fundamental idea to think about it. All right, so these reactions lead to these substitution, these SN2 reactions lead to the inversion, most of the time, at the carbon that bears the leaving group. Now, two warnings about this, two caveats, two reminders. Caveats. Or is it EA? I don't know. Reminders. I get paid to do chemistry, not spelling. That's what my word processor gets paid for. Both of them come from this example, but they apply across the board. Let us suppose I have, let's put chlorine here as a leaving group, and I'm going to react this with iodide. We will talk later on Monday, about why this is a nucleophile, why this is a leaving group, and why methyl is not a leaving group. We'll leave that to Monday. For the moment, that's what we need to talk about. So the SN2 reaction would be iodide coming in, hitting the carbon, displacing the chlorine. So what happens here? Well, the SN2 is happening at, in this case, the stereo center that bears the chlorine, and inversion happens. So when you draw the inversion, something gets flipped. When you do inversion, two things get flipped. Now remember, there's a hydrogen here as well. So it is convenient, especially with rings, to leave the ring in the plane of the board and have now the nucleophile down. The leaving group is up, so the flip would be the nucleophile down. And you can think the nucleophile's got to come in from the backside of the carbon-chlorine bond anyways. Do your transition state models, it'll be a little bit clearer. So there is your inverted center where the substitution occurred, and there is the methyl. So here are the two warnings that come from this. Number one, when this inversion occurs, the inversion does not occur at every stereocenter in the molecule because not every stereocenter in the molecule is undergoing nucleophilic attack. It only occurs where the nucleophile is attacking. So we changed the stereocenter where the leaving group is, but we left the methyl alone. No curved arrows up here, no bond breaking, no change in stereochemistry. Number two, when we talk about the product of this reaction, over here we said these were enantiomers. That's correct. Do not, however, be led to the idea that every single SN2 reaction leads to a product which is an enantiomer of the reactant. As a matter of fact, those cases, well, where the products are enantiomers or where the product and the reactant are enantiomers, those cases are really rare. The vast majority of the time, what you're going to see is the product isn't even going to be an isomer of what we started with. This is a chloride and this is an iodide. They're not even isomers. So we wouldn't say these are enantiomers. These aren't even stereoisomers. And even then, sometimes the products here, they're enantiomers, but they're not always enantiomers. Maybe there's two stereocenters, and in fact, the products are diastereomers, that kind of thing. So when you're comparing the stereochemistry of the products or the stereochemistry of the product and the reactant or something like that, pay careful attention to getting the right vocabulary. Okay, now we're done with that issue. Now, there's something else we need to talk about. I guess we can erase this. One of those things that I know you probably don't want to hear about, I'm going to use one of those bad words. This word. Remember this bad word? How many of you remember that word? How many of you have blotted it out of your mind? Then how would you remember it? If you blotted it out of your mind, how would you know you've blotted it out? It's like people who say, I forgot something. How do you know you forgot it? Right? But anyways, we need to talk about thermodynamics because there is important thermodynamic issues here, but we're going to be very, very simple. If you remember, delta G equals delta H minus T delta S, that's even more complicated than we need to be. We just need to think about energy. Because as it turns out, there was a correlation between energy and rate. You may already be familiar with that. And because we spend a lot of time talking about how the different variables in a reaction influence its rate, we need to understand this connection. So we do it from thermodynamics. And here's the way I want you to think about it. This lump of sulfur has been sitting up here for about 30 minutes. Been sitting in my file cabinet for about another 10 years before that. It's sulfur. Now, why should we care about that? Because sulfur doesn't like to be sulfur. Sulfur, especially when it's bathed in oxygen, likes to be sulfur dioxide. How do I know that? I can do that by estimating what the equilibrium is. And I don't even have to put exact numbers on this. We can figure that out by talking about the H, right? The enthalpy of the reactants. We can get a good feeling for why this is interesting. What is the enthalpy of sulfur at room temperature, pure sulfur at room temperature and 1 atmosphere of pressure? It's a pure element. What's the enthalpy of a pure element in its standard state? 0. What's the enthalpy of oxygen in the atmosphere? Not quite exactly 0 because it's not a pure element, it's mixed with nitrogen, but it's close enough to be 0 that we can call it 0. Now, you don't know what the enthalpy of SO2 is, but if you go and look it up, it's something in the order of about minus 76 kilocalories per mole, approximately. Meaning, if you look at this equilibrium constant, it really, 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 really favors sulfur dioxide by a huge amount. This reaction is thermodynamically spontaneous with a capital spontaneous. It really, really wants to happen. If you listen carefully to the sulfur, you can hear it going, ah! You hear? Right? You hear it? You're insane if you hear it. That's okay. We're all insane in our own way. It depends on how you define insanity. If you define insanity as deviating from the norm, how many of you don't eat tomatoes? You're insane because more people eat tomatoes than not. At UCLA, which do you think has the majority, male or female? Female. Guys, we're insane because we're not the majority. We don't do what everybody else does. I kid you not. All right, anyways. So what's going on here? Why doesn't this piece of sulfur spontaneously become sulfur dioxide? That is because there is a barrier. And this thing was known for a long time. There is a barrier to the reaction. There's some energetically expensive process where that sulfur atoms at room temperature simply just don't have enough energy to become sulfur dioxide. So the reaction is thermodynamically spontaneous, but not kinetically spontaneous. Its reaction rate at room temperature is virtually 0. It smells a little bit like sulfur dioxide, but not to any great extent. So this barrier turns out to be really important because it is that barrier that controls the rate of a reaction. It tells us whether or not a reaction can or cannot occur, how changing variables in the reaction influences the rate, etc. I want to think about the origin of that barrier by looking at our hydroxide plus methyl chloride case that we talked about, the one that I erased before. So let me just, hydroxide plus methyl chloride. There is that transition state again, same one you had before, I'm just redrawing it. And that goes on to make methanol plus chloride. Now what I want to do is I'm going to make a graph of energy that changes that occur as the reaction proceeds. So this thing that I'm going to draw is called an energy profile. I know we're not supposed to profile, but like by saying you're insane because you're male, that's profiling, and I apologize, we're not supposed to do that. Joke. Insert laugh track here. All right. This graph, we're going to plot over here energy. Now, if we wanted to be rigorous, we'd say whether this is G or H or whatever. We're not really going to talk about that. We're just going to call it energy. Whether it's G or H, that's not quite semantics, but we're being simple. So we'll just call it energy. It's one of those thermodynamic entities. This coordinate, the x coordinate in our graph, does not represent time, but rather it represents progress in a set of reactants from being reactants to being products. So we call this the reaction coordinate, like this is the energy coordinate. And so now we're going to put some energies in here. All right, so let's start arbitrarily. Let's put the reactants, just that much energy. The exact amount doesn't matter. So this is methyl chloride and hydroxide. That's my starting point. Over here in the products, I'm going to put their energy somewhat lower, methanol and chloride. And the principal reason for that is because a carbon-oxygen bond is a little bit stronger than a carbon-chlorine bond. You don't need to know that. It's just a fact. So as this reaction proceeds, the energy goes down as we go to the reactants. Otherwise, well, let's look at that energy difference. Here's an energy difference right here between these guys. This would be delta, let's call this G just for the sake of argument, delta G. And what does delta G control in a reaction? How many times in 14B did you calculate delta G because you wanted to measure, you wanted to know what the was? What's the Spontaneity, free energy, equilibrium constant. In other words, the energy difference between the reactants and the products controls equilibrium constant. It does not control the rate of the reaction. It controls, when everything comes to equilibrium, what you have more of. But it doesn't tell us how quickly or how slowly the equilibrium is established. Now I need to put the transition state in here as well. Where's the transition state energy? Let's rationalize that. We can do that. Let's go back to our park bench metaphor. You're sitting there on the park bench. You're all happy. You're chatting with your friends, right? You're tweeting with the people sitting right next to you and say, it's so cool to sit next to you on the park bench. If you can say that in 140 characters or less. But then this other person comes along, and especially if you don't know this other person, they're getting in your space. How do you feel about that? Do I need to do the live demonstration? All right. I need some you want to be a volunteer for this? No? Okay. You sure you want to smell the sulfur? No? Can I just, you guys want to do this? It's real simple. No? You don't want to do it?
No, go ahead. That's fine.
You want to do it? You can come up here. It's nice and simple. Bree's not volunteering because she knows what I'm going to do, right? Good. Come up here, Bree. You guys can be part of this. I want you guys to stand up here, right here. You're going to be like, this is our molecule, right? You guys you've bonded together. You're part of the molecule. So you guys could have gotten to be the nucleophile. I'm the nucleophile. This is the molecule. You guys are perfectly happy. You're methyl chloride, you're methyl chloride. Here comes hydroxide. I'm going to react with you guys, right? How do you feel about this? Because remember, to bond, I've got to get really close. And you've got all these groups sticking out here. How do you feel about that? How does it make you feel?
How you doing?
I'm getting... No, it's not you don't get to ask me questions, you're a molecule. You get awkward. That's a good way to put it. Thank you. It makes you uncomfortable because I am crowding in your space. Thank you. You can sit down now. because I'm crowding in your space. But that's the point. It's crowding. When the nucleophile comes in, these groups move away. Why do they move away? Because they're being crowded. How does that make them feel? Uncomfortable. How does a molecule express its uncomfortableness? It doesn't go, hey! What feature of the molecule changes? Goes up when it becomes uncomfortable. It's potential energy. So as the nucleophile approaches the carbon, this energy goes up, 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 up. Well, let's not draw it as a dotted line. It goes up, up, up. It reaches a maximum at some point, and then the crowding begins to be relieved as the leaving group leaves, and it drops down here. So this point up here, let me erase profile, this highest energy point up here actually is where the transition state is. TS, abbreviation for transition state. That actually, by the way, is our definition of transition state. Transition state is the highest energy structure in the mechanism step between the reactants and the products for that step. Highest energy structure, which means if you have multiple steps in your mechanism, you have multiple transition states. Now this energy difference right here, the difference in the energy between the reactants and the transition state energy, we're going to give that a name. It's the delta G, since we're using a G scale, but it's the transition state energy, so we call it delta G double dagger. First for mathematical reasons, but for kind of chemically logical reasons that we'll do in a second, this thing controls the rate. It is the height of this hill that controls how quickly the reaction occurs. Here's how that works. Let us imagine at the end of class you want to leave CS50. I can't imagine you want to sit in here for the rest of Friday afternoon unless the class afterward is interesting or you're enrolled in it or whatever. Now, the rate at which people leave the class, there's a certain amount of time that the entire classroom will take to be emptied out. People leave at different rates, partly depending upon where you're sitting, but also how steep the stairs are. And both of those things matter. How steep the stairs are means the people in the front go, oh, these aren't very bad. I can do this. Now imagine the stairs are like this. You go, oh, it's Friday afternoon. I've had to sit through 14D and being called insane because I can smell the sulfur. Now I got to climb these stairs. Oh, I'm not picking on you. And you take forever to get out of the room. People sitting in the back will get out quicker because their distance to the top of the energy hill, the top of the stairs, is not as much. Now, the further you are down on the hill, and the steeper the hill is, the longer it takes the room to empty out. So let's change these steps to this curve, the amount of energy that you have to pay to climb over that hill, and your position is your relative amount of energy. Remember that in a reaction, the reaction has a temperature, but that temperature is average kinetic energy. Some molecules moving faster, some moving slower. Molecules that have more kinetic energy have a greater possibility of being able to climb over that hill when they smack together. The more probability there is that a collision is productive means the reaction's faster. So in other words, this hill controls the rate. Now mathematically where that comes from, before people started drawing things like this, somebody was working with the math and said, hey, look what I've discovered. Something called the Arrhenius equation. You may be familiar with this thing. Anybody remember Arrhenius equation? Right? I hear people hissing. Arrhenius equation says this. K equals, let me get all my right variables and constants here. C e to the minus RT, delta G over RT. Well, let me be a little bit more precise since it's not quite delta G. Let me talk about what everything is here. So this is the Arrhenius equation. It says K. This is the K in a rate expression. So when you say rate equals K times stuff, that's what this is. Big C is just a constant. E is the natural log base, E. Minus EA. Now EA stands for energy of activation. And outside of some thermodynamic conventions, for all intents and purposes, is the height of this hill. There's some subtle differences, but we're going to use it for that. Divided by R, the gas constant, T, temperature in Kelvin. What does this expression say? It says that the rate of the reaction is a function of this energy difference plus the temperature. So it's a negative exponent. What happens with a negative exponent? When this number gets bigger, push buttons on your calculator if you don't know. When this number gets bigger, because it's a negative exponent, when it gets bigger, this rate goes down. So in other words, in terms of the variables that are involved here, the rate goes down when the energy of activation, or the delta G, double dagger, whatever you want to think of it as, but that energy difference between the reactants and the transition state, when these go up, the rate goes down. And by the way, we know that. Actually, not quite. There's the other thing we know. I misspoke myself there. The other thing we know that influences the rate, that makes the rate go down, is that temperature in Kelvin. That's here in the expression. It's a negative exponent, but it's a reciprocal. So what happens when, to the rate, how do we make the rate go down? What do we do to T? Make it go down. Lower temperature means lower rate. Now that one we know, that makes a certain amount of sense. If you want the rate of this sulfur becoming sulfur dioxide to go up, what do you do to it? Right? If you wanted to convert sulfur to sulfur dioxide, if you wanted to oxidize sulfur to sulfur dioxide, you want to do, well, combust it. What would you do? You take a flame to it. You heat it up. And that's what's going on here. It's basically saying, in the SO2 case, there's a whole bunch of hills here because it's a multi-step mechanism. The first hill is really big because the first hill happens to be taking O2 and breaking it apart into two oxygen atoms. But if you add enough energy, then the O2s break apart quickly enough that the whole process can get started. So we know that by adding temperature, you make reactions. Most reactions go faster. There are some that go the other way around, but they're not common. So this is why we're interested in the transition state structure and relative to the reactants, because this energy difference tells us about rate. Any manipulations we make, any changes we make to reactants or transition state can influence the rate of the reaction. All right. Now, I want to talk about kind of a biological thought on this. And that is something we probably already know about. And that is how enzymes are involved in this. Enzymatic catalysis. Remember what enzymes are. Enzymes are usually proteins whose job it is to go around and do other reactions, but to make those reactions much faster. So they catalyze reactions. And they do it by manipulating, among other things, by manipulating this energy difference. This was Linus Pauling's idea, by the way. Remember Linus Pauling resonance? Remember Linus Pauling hybridization? Remember Linus Pauling electronegativity? Remember Linus Pauling, gosh darn it, DNA is in a triple helix? Remember Linus Pauling too much vitamin C near the end of his life? Remember Linus Pauling, I think he won a Nobel Peace Prize? Linus Pauling, Caltech, Linus Pauling. Let's draw an energy profile just for a typical reaction. There it is. The rate of this reaction, whatever it is, doesn't matter. It could be an SN2 reaction. Has this delta G, we're going to call that delta G double dagger number 1, because this is pathway, or this is reaction number 1. Now, to make this reaction faster, there's a whole slew of things we can do. But one of the proposals is that an enzyme will either stabilize the transition state. So maybe we'll put that in dotted line. The enzyme stabilizes the transition state, lower energy, and or it can, and we'll do both here, destabilize the reactant. So it can raise their energy by maybe changing their conformation and making them uncomfortable, that kind of thing. But the point is, by doing one of those two things or both, we'll use the dotted line to see that. We're going to do the same product, so we'll end in the same place. But now we have, we'll use dotted line again. There is our delta G for the 2. And we're saying number 1 here is not catalyzed, uncatalyzed, and 2 has the enzyme present, the catalyzed. That doesn't mean there's a cat present. That means catalyzed. It doesn't mean if you're doing an SN2 reaction and you throw in some famous cat, that it's going to go faster. That's not what I mean. Schrodinger's cat. Yeah, let's throw in Schrodinger's cat, right? I was trying to think. Thomasina was the cat I was trying to think of, the famous Disney cat. But what it says is because the enzyme makes the reactants less stable and or the transition state more stable, It lowers that energy of activation and makes the reaction faster. Now, enzymes do all sorts of other things to make reactions faster, but that's one of them. Now, we are now at a point where we can begin, we have the ammunition to think about changing variables in an SN2 reaction and how does it influence the rate. So we'll call these our SN2 variables. Now what I want to do here is in a very generic sense write an SN2 reaction. Nucleophile, R3 carbon leaving group. So remember, R group is just a generic group. It's often a carbon group, but I don't mean it to be limited that way here. We're just saying 3 things attached to carbon that aren't the leaving group. We're not specifying what they are. Nucleophile attacks the carbon, same time the leaving group leaves because it's SN2. That takes us to our product, nucleophile CR3 plus the leaving group. I'm not putting in any charges because I'm being generic. I don't know what the nucleophile is. I don't know what the leaving group is, so I can't specify their charge. But in looking at this, we can begin to think about some of the kinds of variables, the things that if we change in a reaction, how might it influence it. One of them, and this is the order we're going to talk about them. First, we're going to talk about the nature of the nucleophile. What's the nucleophile's job? We're not going to do it today. What's the nucleophile's job? How does changing the nucleophile influence the rate of the reaction? What structural feature do we focus on? Number 2, we're going to talk about the nature of the leaving group. What is it about the leaving group? If we change its structure, makes it faster or slower? Think about that in terms of what is it doing in the reaction? How are the electrons flowing? Those 2 things we're going to talk about on Monday. Wednesday, we're going to talk about the nature of the things attached to the carbon. And then something which is not written up here, which is the solvent. The stuff that the reaction is dissolved in turns out to be critically important as well. So that's what I want you to do over the weekend. Think about the role of the nucleophile. What's it doing? What's it supplying, etc. And how would changing its structure influence its ability to do that? See you Monday.